we were discussing superposition of states, isn't it? I better to say like that. Not only in case of particle passing through double slit, okay? So in the most general case, we were talking about superposition of different states, isn't it? Superposition of different translation state in case of particle in double slit, okay? Superposition of different momentum state in case of single slit diffraction experiment when the slit width is very small, isn't it? Again, look at here, this superposition state so it leads to indeterminacy. So not only that, okay, not only this superposition state, okay, I think we have a lot of other ideas, isn't it? In case of, again, you can't do any measurement without disturbing the system, isn't it? So those things also gives the similar idea actually, but the superposition state gives the again it what you call imposes a kind of indeterminacy in quantum mechanics. That okay, indeterminacy means in classical mechanics, before you do the observation, you can say that this is going to happen. It's going to be the what you call its momentum. It is going to be its kinetic energy. It's going to be its energy, isn't it? We can say like that. Then after that we can observe. And one more thing, in case of classical mechanics, we can observe on the same system repeatedly. Our observation is not disturbing the system, or whatever the disturbance we do while observing, that is negligible. So that's why again. So you should remember this one also. In case of classical observation, you can take the same system. You can do repeated measurement. But if you take a quantum system, so small object. So what is happening is each of your measurement is disturbing the system. So that's why you have to take identically prepared system. All systems which are prepared with the same state psi. Okay, and you should do the measurement on each. Then you have to verify that probability. You can't do the measurement on the same system, because first measurement itself will disturb the system. If you are doing second measurement, you are doing it on disturbed system, not on the fresh system. But classically, if you do the observation that disturbance is negligible, it is fresh only. Is that okay? Its states are not what you call changed because of your measurement. Its momentum, position as a function of time, that is not going to change because of your measurement. Is that okay? But here it will change. That's the one idea. Okay, classical observation, quantum mechanical observation, you should know exact clear-cut difference. So in quantum mechanical observation, you should take identically, again, by only one measurement, you can't say anything, isn't it? So now you say probability of being head is half, isn't it? Let me try to build something here, then I'll go to that one. So now how do you convince that one? With only one toss, can you convince that one? With only one toss, can you convince that probability of being head is half? No, isn't it? You need to do lots of, again, yes, exactly in the same way, again, to convince any probability stuff, okay, you need to have what you call many measurement. But the problem with quantum mechanics is each of your, again, coin you can toss same coin so millions of times, isn't it? So it is not changing its shape or something, isn't it? But when you come to what you call quantum mechanical system, each of our measurement is disturbing the system. So that's why again to what you call to convince any probability stuff. Suppose if you say that probability of being head in case of coin is half, isn't it? You say like that, okay? Suppose if you toss the coin twice, unfortunately if you get both tail, then what I will say? You are lying. So probability of being tail is 1, probability of being head is 0. Is that true? No. Then what you have to do? So then what you have to do? You have to increase number of trials, isn't it? You have to do it 100 times. You have to do it millions of times. If you take infinitely many trials, so then the ratio of being head divided by total number of trials, that will close to half, or that will be almost nearby half. Is that okay? That's how we need to convince. But in case of classical system, just like coin and all, you can take the same what you call system and you can do repeated measurement. Is that okay? So if you do first measurement, it's not going to disturb the probability if you toss the coin next time, isn't it? If you toss the next coin, so next time if you toss the coin, again it is half and half, isn't it? Are you getting my point? So that's why it's not going to affect our next toss, isn't it? But in quantum mechanical system, if you do the first measurement, it is disturbed too much. It's going to affect our next measurement. I mean, our next measurement is on disturbed system. That's why you need to take identically prepared system, millions of identically prepared system. We call that as ensemble of identically prepared system. And we need to measurement on each, okay? And we need to take the measurement outcome, and we need to talk about probability. We can verify the probability. Okay, so that is the difference between classical measurement, quantum measurement. Okay, so now look at here. This superposition state, it led to a kind of indeterminacy, isn't it? So again, if you take in case of double slit experiment, okay, slit 1, slit 2 here, your state was like that. Am I right? Your superposition state was psi 1 plus psi 2. Superposition of two translation states. You don't know. Before, again, indeterminacy means before measurement you don't know. But in classical mechanics, before measurement also you know. You have solved what you call Newton's second law. Again, you can predict what is going to happen, isn't it? Not any probability. We can 100% say that this is going to happen in case of what you call classical physics. But this indeterminacy means before measurement we don't know through which slit electron is passing through. If you do the measurement, there are two possibilities. Whatever the electron reaching the screen, they have two possibilities. If you do the measurement, they will be either passing through slit 1 or passing through slit 2. But if you are not doing the measurement, it is in the superposition state. Again, you can't say anything about that one without doing the measurement. So similarly, we have seen one more aspect. Am I right? Single slit diffraction. So electrons, what you call, they had range of momentum. Am I right? They had range of momentum. Can I say Py1, Py2, Py3, Py4, Py5, y component of momentum is different, isn't it? Yes. Again, it has continuous range actually. For convenience, I have written like that. Later we shall go to what you call integral kind of thing. Okay. So state of our particle. So that is a superposition of different momentum state. Can I say like this? Each of this stream, each of this line talks about one momentum state, definite momentum state. Because of that definite momentum only, it reached that position in the screen. Okay? So that's why the state of the particle is psi Py1 plus psi Py2 plus psi Py3 and so on. The best idea is to write this one as an integral psi Py dpy like that. We shall see this one, okay? We shall see this mathematics later, but again, so this is also superposition state. That's what you need to convince yourself. If you see this state as a superposition of momentum state, it contains range of momentum. If you see this state as a superposition of position state, y position state, it contains some range of y position, but very less. So that is regarding uncertainty. I am not worried about uncertainty here. I am worried about what is the consequence of superposition state. So the consequence of this superposition state is we don't know what is next electron is going to take the path, isn't it? We don't know what next electron is going to, which path next electron is going to choose, isn't it? We don't know that one. That is indeterminacy. We don't know what is next electron, again, whether the next electron comes from slit 1 or slit 2, isn't it? We don't know that one. That is indeterminacy. And we don't know what is the next electron at which position of this what you call small width it's going to pass through. That means what is its y position. In y also it has little uncertainty, okay? But that uncertainty is small in this case. Uncertainty in Py is large here. Okay, that you can see here. The superposition state leads to indeterminacy. We can't say before measurement. Okay. Now let me make it quite simple. So now look at here. It's a kind of indeterminate. Before measurement, we don't know, isn't it? Suppose if you toss the coin, okay. Again, before that coin comes to the ground, you don't know whether it's going to be head or tail, isn't it? Suppose if you toss a dice, before it's going to what you call so take rest, okay. So you can't say whether it is 1, 2, 3, 4, 5, 6, isn't it? Dice, okay, in case of dice. Suppose, suppose let me take one more small example here. Suppose if you are saying that I don't know whether I am going to attend this class or not, isn't it? I don't know. Now look at here. I can ask you. Yeah, we don't know. Again, only after you attend class or after that time we will get to know whether you are attending that class or not, isn't it? We don't know. Okay. So at least you can say what is the probability. Are you getting my point? Yes. Now, if a superposition state imposes indeterminacy, at least we can talk about probability of outcome. You say, I don't know whether head is going to come or tail is going to come, isn't it? You say, I don't know whether I will get 1, 2, 3, 4, 5, 6 in case of dice or not, isn't it? Is that okay? You don't know that one, but at least you can talk about probability of the outcome, isn't it? Our wave function will give the will give the information about probability of measurement outcome. This is called as wave function. Look at here, it has two names. Okay, one is probability density. This psi. Okay, so another one is wave function. Another one is wave function. Is that okay? So now, if you see this word, you will definitely get to know its role is to define probability stuff. Okay, but if you see this word, it is quite misleading. Maybe all of this theory again developed by Schrodinger by thinking it has a wave only. Are you getting my point? It has a wave nature, but it is following some different natural thing. Okay, but this wave function again is a quite misleading term. It is not talking about your de Broglie wave. Okay. It is not talking, again, it will not give the amplitude of any real electric field, magnetic field or something. Is that okay? This wave function only, again, it will give the information about the probability. If you say it is indeterminate, you should at least talk about probability of measurement outcome, isn't it? You just at least say whether you attend the class or again, what is the probability of attending class, what is the probability of not attending class, isn't it? And that information is given by this psi, whatever we are writing here. Okay, suppose if these two amplitudes are same, and in the linear superposition, suppose if these two coefficients are same, okay, later we try to normalize by putting 1 by root to psi 1 plus psi 2 like that. Okay, same coefficient like that. So then you can say that so probability of getting electron in slit 1 and slit 2 same, isn't it? You can say like that. Are you getting my point? Now again, so in this one, look at here, more electron will move here, isn't it? More electron will move here. Less number of electron will move here. Because of that, you have minima here, you have maxima here, isn't it? So you can talk about probability of again, if you do the measurement, what is the probability of getting the electron here? What is the probability of getting the electron here? That means what is the probability of getting py1? What is the probability of getting py2 and so on, isn't it? This is not discrete probability, this is continuous probability. I will convince later, okay? But I have taken it as discrete for my convenience, okay? Isn't it? At least you can talk about that one. And wave function contains that information.
Sir?
Is that clear? Yes.
Sir, your integration is over all space.
Speak out. Speak out again.
Sir, your integration is over all space.
No, this is dpy, different momentum state. I'm expanding this one in terms of momentum state. Don't think about mathematics right now. Okay? I'll convince this one. I'll convince this. This is not position integration. Okay? This is not position integration. This is integration with respect to momentum. Okay? Again, suppose if you take this experiment. Is that okay? So this is y here. So this is delta y here. Is that okay? This one. So then almost everything have got same momentum. Am I right? Delta py is very small. In this case, your state is it has well-defined momentum. Okay. In this case, it has little bit well-defined y component of position. Okay. But this state, whatever state you prepare, it has ill-defined position, y component of position. I am going to write like this, psi y1 plus psi y2 plus psi y3 plus and so on, that's equal to some integral of psi y dy, isn't it? Yes. That dimensionally not correct, but I'm writing for comfort, okay? The same state, the same state you can write it as psi py1 plus psi py2, but these py's have a very less range in this case. This py have got large range in this case. That is because of uncertainty. Okay, I am not concentrating on uncertainty here. I am concentrating on how superposition of state happening here. Okay, just again, if you think about, if you think that state is superposition of position state, if you write the state as superposition of momentum state, then you can talk about uncertainty. Okay, to talk about uncertainty, the same state I have expanded in terms of different thing. Is that okay? Yes, wait one second. This state, look at here, this state, so it has very less y1 plus psi y2. This range of y's are very small for this one. The range of y's are very large for this one. Okay, the range of py are very large for this one. Okay, so the range of what you call py is very small for this one. Almost every beam have got what you call 0 py, isn't it? Yeah. Now ask the doubt.
Sir, momentum state are also the continuous states of these all are.
That is continuous state only. That is continuous state only. I am saying I'll explain this mathematics later. But it's also superposition state. Because of that superposition state, that indeterminacy happened. What indeterminacy? I don't know which y position. So through which y position this electron is passing through. I don't know which direction electron is going to take. But at least you can say what is the probability of it, isn't it? At least you can say what is the probability of getting py4, what is the probability of getting electron exactly at this position, isn't it? On the screen. That information is there in the wave function. Okay? That information is there in the wave function, and wave function gives only that information. It will not give you what kind of wave it is. It will not give you whether it has wave behavior, particle behavior.
So it's dependent only on amplitude?
What amplitude?
I mean, you are saying that if the amplitude are same.
I see, in this case I told about amplitude here. In this case, suppose coefficient. We say coefficient. We will learn this one. How that probability stuffs are defined in quantum mechanics. You are going to learn that one. But what I am saying is, this wave function that contains that information of probability, and use of wave function is only to what you call define the probability, nothing else. It is not, even though the word contains wave, okay, even though wave function this contains wave, it's not going to convince you what kind of wave it is. Okay, it's not going to give you whether it's a particle or wave. It will give you only information about probability.
Sir, can you explain why psi is complex?
Because our wave function is complex, we shall see. Our Schrodinger equation is complex. We shall see that one. Okay. One thing is, look at here. Prior to define probability, you needed to define something whose mod square, again, whose square is probability, isn't it? We don't know what it is. That's why let it be complex. That is one idea. Is that okay? Other idea is, again, we shall see now. Again, I'll give the hint for how Schrodinger equation might have found. The Schrodinger equation itself contains I and all, isn't it? And it's a solution of Schrodinger equation. Again, wave function, the best definition is it's a solution of Schrodinger equation. So, solution of differential equation can be complex, isn't it? Now, let me move on here. That's why our next aim is to find what is this wave function, how to get that wave function, isn't it? Look at here, our double slit experiment itself gives a lot of hints. Okay, double slit experiment gives us lot of hints. How do we get psi, isn't it? Psi, which contains all information, all probability information. Okay, in quantum mechanics, only you can talk about probability. Without measurement, you can't say anything. Okay, only after measurement only you will get some of the possibility. Again, you have possibility. You have one possibility that you are going to attend the class, other possibility you are not going to attend the class, isn't it? Now, again, you can talk about what is the probability, isn't it, of those possibility.
Yes.
Probability of possibility, isn't it? Probability of possible outcomes. So that information is there in the wave function. And how to find that one? How do we get that one? Okay. I said wave function contains all probability stuff inside that one. Okay. Now what I do here is I'll take 1 millionth of identically prepared system. I told you in case of quantum mechanics you need to take identically prepared system. I'm going to take 1 millionth of identically prepared system. Okay. Again I'm going to take other 1 million. 1 more million of identically prepared system. So all of these 2 millions of systems, they are prepared in the same state. Why I have taken? So that I can do the measurement and I can verify the probability. To verify the probability, you need large number of trials. You can't do the measurement on the same thing. That's why I have taken millions of identically prepared system. Identically prepared means all systems are prepared with the same size, same state. Okay? Are you getting my point? That's the idea. Now look at here. So what I do is at a time t equal to 0, I am going to do the measurement on this first million. And I am going to find some what you call probability stuff. So that I am going to verify what is psi at t equal to 0. I say psi at t equal to 0 is giving some probability information. Am I right? How do you verify? You should do the measurement at t equal to 0 and you have to verify, yeah, this size talks about those probabilities, isn't it? If you take millions of experiment, you will get the probability, isn't it? Are you getting my point? So what I do is for other million which are identically prepared, I am going to wait for some time. I am going to do measurement after some time. I am going to do measurement after some time.
On the same system?
Identically prepared. At t equal to 0, both are identically prepared. But here I am going to wait and then do the measurement.
Okay.
Then your probability outcomes may change. Isn't it? Probability of measurement outcome may change with respect to time. Am I right? Are you getting my point? This wave function can change with respect to time in the most general system. Are you getting my point? That is represented by wave function at later time. That information is given by wave function at later time, isn't it? Yeah, we are talking about probability. Wave function gives the probability of measurement outcome, isn't it? That probability also may change with respect to time, isn't it? That means wave function is changing with respect to time.
Yes.
That's why after some time, if you do the measurement on millions of system, ensemble of system, you may get different probability ratio. Are you getting my point? Here you may get different probability ratio. That means our wave function can change with respect to time, isn't it? Similarly, position can change with respect to time. Momentum can change with respect to time, isn't it? Now, if you know position and momentum at one instant of time, how do you find position and momentum at other instant of time? You should go for Newton's second law, isn't it? Are you getting my point? You should go for Newton's second law. So, in case of Newton's second law, that's a differential equation, isn't it? Whatever law you take in case of physics, radioactive law, Newton's second law, your Kirchhoff voltage law, most of the laws are, we held that one by a differential equation, isn't it? Similarly, we are going for one more differential equation here.
Okay.
When you solve that one, it will get wave function psi as a function of t. Okay? We need a connection, we need an equation which connecting these two. Okay? Which is connecting these two. We need an equation. When you solve this one, it gives psi.
Yes.
So that is the basic idea.
Sir,
Yes.
so you said that in classical mechanics position changes with respect to time, and here also wave function changes.
Yes, true.
Sir, position can be at rest in classical mechanics. It doesn't.
No, here it is not possible. I'm not saying it is same as that one. Is that okay? I'm not, again, in quantum mechanics, look at here, that we have seen that superposition states, am I right? You can't have definite position state, you can't have definite momentum state at all. Before measurement, you can't say the particle is not going to be there here. X as a function of t, it doesn't exist. Position and momentum variable doesn't exist in quantum mechanics. Are you getting my point? That's a very good question. So in classical mechanics, okay, we say what is the position as a function of time, momentum as a function of time. No, here we can't talk about that one at all. Okay, We can only talk about probability of position measurement outcome, probability of momentum measurement outcome. You can only talk about that one. Before measurement, you can't say anything. Is it clear? Yes.
So wave function cannot change,
Yeah.
function cannot be in place.
Wave function plays similar role, but it will not give that information what we get in classical mechanics. Is that okay? Now look at here, to find that what you call equation, differential equation, what I do is I'll go for we need a differential equation expressing connection between wave function at one instant of time and wave function at other instant of time. Is that okay? And role of this wave function is only to give some probability information. Okay. Now what I do here is I'll go to, because that double slit experiment mathematics that we copied from optics, am I right? Whatever happened in optics, that should have happened in case of particle also, isn't it? The same functions should have played the role, isn't it? Even though we say wave function here, they are wave amplitude, isn't it? Electric field amplitude, we say probability amplitude here, isn't it? In case of electron double. But since the pattern is same, the functionalities also should be same, isn't it? Psi functionality should be same. If that function is same, mathematical function is same, then we will get the same outcome, isn't it? So that's why what I do is I am going to take similar idea to what you call give the what you call how what you call Schrodinger equation might have found. Okay. Again, in case of wave optics, let me go to wave optics first. Okay. In case of wave optics, again you had two entities. Am I right? Wave from slit 1, wave from slit 2. Or in case of wave optics, okay, whatever superposing, you had two entities, one wave, other wave. You say two things. But in case of quantum superposition, you talk about one particle. Are you getting my point? In case of quantum superposition, we talk about one electron which is in the superposition of states. Isn't it? That's how we say.
We are passing one electron or loss of electron?
One electron. Take one electron experiment. If you explain that one, that's done. Okay. In case of quantum mechanics, again, in case of optics, we are talking about two entities. One is superposing on other in space and it is giving maximum minima like that, isn't it? We had two entities over there which are superposing. But we have only one entity, one electron here, one particle here, which is in the superposition of states. That's how we say, am I right?
Yes.
These all experiments are true for single particle experiment also, isn't it? So that's why, look at here. Suppose in case of optics, how do you write that wave equation? Dou square psi by dou x square. Let me write one dimension, okay? Let me write E or something, psi or psi, okay? Let me write psi. Psi, is equal to 1 by v square, dou square psi by dou t square, am I right? Now let me write v1. Suppose one of the wave, it has some direction or some velocity or something, okay? So dou square psi by dou x square is equal to 1 by v2 square dou square psi by dou t square, okay? Let me write psi 1 here, psi 2 here. I am talking about two waves, okay? Those two waves are the solution of two different differential equations. Two waves which are superposing, they have different direction, isn't it? They have different parameter. They may have different parameter, isn't it? Are you getting my point? You have two entities, two waves over there. Again, I'm trying to touch this one too. I mean, I'm trying to help you to come out of that common sense actually. Okay. In case of wave optics, our common sense works. You had two entities, one wave, other wave. Okay. You had two entities. Okay. Suppose this is electric field amplitude, whatever you take. Okay. So now look at here. This psi 1. So again, one wave have got velocity v1, other wave have got velocity v2. Or one wave may be moving in one direction, other wave have got another wave vector. Wave vector will talk about direction, isn't it? And they are superposing at some point in space and all. Okay. Now look at here. This psi 1 will be function of v. You know that one is equal to x minus vt, v1t. Am I right? The solution of this one of this type of function actually. We are going to study in electrodynamics. Okay. So similarly, solution of this psi 2, it will be x minus v2t. You have one wave, you have two waves, they are superposing, even though they have different velocity or something, yeah, and you are getting some result. Yes. This is optic superposition principle. Okay. But in quantum mechanics, we have the same entity. One electron which is in the superposition of states. Are you getting my point? One electron which can be in the superposition of different velocity state. One electron which can be superposition of different momentum states. Are you getting my point? So in case of single slit diffraction, that state was superposition of different momentum state. One entity which is in the superposition of states, or if superposition is the word which is confusing, you talk about linear combination of states. Linear combination, because that is linearly combined, summation or integration, isn't it?
Yes.
So that's why find the difference, okay? Find the difference. Here we need only one differential equation for one entity. We are talking about only one entity. So again, that entity can be in the superposition of different what you call velocity state, momentum state, position state, energy state, isn't it? Now that, if you look at here, so this differential equation contains the information about motion, velocity. That's why its solution is sensitive to that information. That's in the solution that this will come. This differential equation contains the information about motion of the wave, isn't it? Velocity is one of the parameter of motion of the wave. That's why in its solution that parameter came, parameter of the motion. Okay, but we want to have a solution, okay, which is superposition of many of those parameters. Are you getting my point? Which is superposition state of many of those parameters. So then if our differential equation contains this kind of parameter, then your solution will be sensitive to that one particular value of that parameter. It can't express superposition of states, isn't it? Suppose if my differential equation contains that parameter of motion, suppose again I have some differential equation, it contains what you call Py1.
Sir, please repeat again. Sir.
Wait, let me explain it here. I have some differential equation which contains so Py in my differential equation. Is that okay? Then my solution of that differential equation contains only one of that one. My solution represents only one of this value. Only one of this value. It can't represent a range of that value. That's why that value should not exist in the differential equation. Differential equation should not contain any parameter of the motion, like here. Once it contains any parameter of the motion, your solution depends on that parameter. That solution is only, no, this solution is only for this velocity.
Yes.
This solution is only for this velocity.
Yes.
But we need a solution which corresponds to range of those values.
Okay. We are not specifically said that this will.
Yeah, we can't say that this solution talks only about one of the parameter of the motion. If we say like that, we can't do any superposition of states.
Yes. Yes.
Okay? To allow superposition of state only, we need to deviate from this differential equation. Because here we had different entities. We had again, so even though we had different parameters of the motion, we are not worried, am I right? Those are different entities which are superimposed. But you have only one entity here. Okay? So two things here. So we have two waves. Wave 1, wave 2. Okay? But we have only one particle here. Is that okay? And observe this one, how this solution is sensitive to that parameter. Obviously, if that parameter is there in the differential equation, that parameter will come in the solution. Once it comes in the solution, now look at here, this wave function will never explain any wave traveling with velocity v2, isn't it? So similarly, this solution cannot explain wave which is traveling with velocity v1, isn't it? Those are different. But we need a differential equation that differential equation should not contain any parameter of motion. If it contains parameter of motion, in our solution that particular parameter will come, that particular value will come. And we can't talk about range of that parameter. We can't talk about superposition of those different parameters, isn't it? That's why our differential equation should not contain any parameter of the motion. So you write down this statement. You write down this statement. The equation must have two basic properties. Are you getting my point? Suppose, look at here, I have some differential equation, some d square dou square by dou x square something, okay, psi, some px square or something, okay, you have something, okay. Then what happens, your solution will be sensitive to that parameter. This solution can talk about only one momentum, isn't it? It can't talk about superposition of momentum states. It can't talk about wave which is traveling with other velocity, isn't it? It can represent only wave which is traveling with velocity v1. This differential equation solution. Is it okay? So that's why this is the target. We need to avoid any parameters of the motion so that we will open that one for superposition of states, superposition of different of those values.
Sir, if we have superposition of the solution of the superposition, then how do I convince that superposition is also a solution of the wave function?
No, that's why again one thing is we are going for linear differential equation, which allows that superposition is also solution. That's I told yesterday, isn't it? We are going for linear differential equation, not non-linear differential equation. Linear differential equation have a mathematical property that if you have two solutions, if you add those two solutions or if you linearly combine those two solutions, that is also solution. We shall see that one. Yeah, equation should be linear differential equation. And equation should not contain parameter of the motion. Equation should not contain some particular position, some particular momentum. If it contains like that, its solution will depend on that one. You can't talk about superposition of position. You can't talk about superposition of momentum state. You can't talk about superposition of energy states. Are you getting my idea? Yeah. The equation must have two basic properties. Okay. First, equation must have two basic properties. First one, it must be linear. You told, isn't it? How do you know that our equation allows superposition of different states, isn't it? It must be linear differential equation. Linear, you say it must be linear. In order that solution of it can be superposed, to produce interference effects. Solution of it can be superposed to produce interference effects or superposition effect, whatever you say. There are some effects of that superposition of state, am I right? So to produce interference effect, because while finding this Schrodinger equation, they were talking about wave theory only, okay? Wave theory, wave nature, like that only, okay? While formulating that one. Now we have some deviation here, okay? And second one, the coefficients that comes in the equation or constants that comes in the equation must involve only constants, like h bar, mass, because we are talking about non-relativistic theory, mass is not variable here, okay? Constant, h bar, mass, charge.
Involve only constants?
Must involve only constants such as h bar. Wait, which one?
Mass.
Equation must involve only constants, okay? Such as mass, h bar, Planck constant, charge, like that. And equation should not involve any parameters. Equation should not involve any parameter of a particular kind of motion. Are you getting my point? That means particular kind of motion is particular momentum, particular position, particular energy, like that, okay? Equation should not involve any parameter of a particular kind of motion. Momentum talks about some kind of motion, am I right? It's a parameter for motion.
So it will not include speed of light.
It can include speed of light. Speed of light is a constant, universal constant, but not velocity of particle. That's what I'm saying. Okay? Yeah. This is sufficient. We shall quickly get into that one so that in the next session we can start dealing with this. Now look at here, we have seen that again the mathematics behind our optics interference and electron interference are same. Look at here. So that's why what I do is the similar function should be followed by the particles. Okay, let me assume like that. We call this as plane wave solution. A e power I kx minus omega t. Okay, kx minus omega t. So according to our wave, look at here, E is equal to h bar omega. Am I right? Wave idea, isn't it? E is equal to h bar omega, and we are going to write again E is equal to, again according to our this is a kind of merging of particle and wave behavior. Okay, let me try to write a note. Last time I couldn't write a note on this one. Yeah, let me try to write a note. One more thing is E is equal to p square by 2m also. It's a kind of merging of particle and wave things. Okay, here. So p is equal to h bar omega, h bar k. P is equal to h bar k according to our de Broglie hypothesis. So according to our wave idea, E is equal to h bar omega. E again, so this is a free particle now. You are talking about particle in double slit, which is a free particle. You don't have any force here. Is that okay? So that's why we call this as plane wave solution. Okay, in case of our wave optics also, we call this as plane wave, plane monochromatic wave like that. Okay. Now look at here, what are the parameters of motion? This k which decides momentum, this omega which decides energy. These are the parameters of the motion. Omega and k are parameters of the motion, am I right? Obviously, suppose if you talk about wave differential equation, it was like the dou square psi by dou x square is equal to 1 by v square into dou square psi by dou t square. Okay. So now here we write, how do you define omega and k relationship? V into k? Isn't this is equal to, look at here, 1 by v square. What is v square? Yeah, what is 1 by v square? K square by omega square, dou square psi by dou t square. Am I right? Dou square psi by dou x square, that's equal to this one. Now I'll say that this is a solution of this one. This is a solution of this one. But look at here. So our differential equation should not contain this kind of parameter. K, omega, which are parameter of motion. Because the same differential equation should able to give the solution of different of these parameters. This differential equation will give only this one, k1. You just write k1 omega 1 here, isn't it? But our differential equation should able to generate one more solution of different k1 and omega 1, isn't it? That's why this parameter should not exist in our differential equation. That's why we are going to deviate little bit. Here it is second derivative with respect to position, second derivative with respect to time. Am I right? So now look at here. We are going to deviate here. We are going to find the differential equation so that these parameter should not come into our equation k and omega. Okay. For that, what we do here is, look at here. Yes. Yes. If you take with respect to time, what will happen? Minus I omega into psi itself. Can I write like this? Is that okay? Dou square psi by dou x square, second derivative. Ik will come out twice into psi itself. Is that okay? Now I will try to take the ratio. Dou psi by dou t whole divided by dou square psi by dou x square. Okay, it's a kind of fixing kind of thing. Okay, minus I omega ik into ik. One of the I got cancelled. Omega by k square, isn't it? What is this one? I'll take I into numerator, multiplying divide by I. Okay. If I take I to numerator, or I'll keep I in the denominator itself. Wait a second. Or yeah, I'll keep I in the denominator, minus omega by I into k square, isn't it? Now from this equation, I'll try to find some equation. E is equal to h bar square k square by 2m. Am I right? Now h bar omega is equal to h bar square k square by 2m. I'll cancel out one of the h bar. Omega by k square. That's equal to h bar by 2m. Am I right? Just check that out. Minus 1 by I h bar by 2m. Is that okay? Now again, earlier we have taken second derivative with respect to time, second derivative with respect to space. Okay, I call this one a time derivative, space derivative. X is spatial coordinate. Okay, so we try to link them so that we got velocity in our differential equation. Okay, that is wave equation, wave optics. Okay, but here we have taken first derivative with respect to time and second derivative with respect to space, so that we can write this ratio as something else. Which is a constant. Is that okay? Which is a constant. So now look at here. Now I am going to rewrite this equation. So I will take it here. I into dou psi by dou t is equal to minus h bar by 2m into dou square psi by dou x square. It doesn't contain any particular parameter of motion. Is that okay? Yes. Now I am going to multiply with h bar. I h bar dou psi by dou x. Now look at here. Psi is a function of x and t. Have you seen? Okay. I h bar dou psi x comma t. Wait a second. I am going to use different symbol later. Okay. I should have written big psi here. I'll write big psi here. Later I will write small psi, that is time independent equation, x comma t by dou t, that's equal to minus h bar square by 2m. Maybe this might have done later, okay, multiplying by h bar. How do you know we have to multiply by h bar, isn't it? We don't know how exactly this equation is found. So Feynman himself says Schrodinger equation comes out of mind of Schrodinger. Intuitive equation, okay. But for our comfort, we are trying to derive the equation. For free particle. Wait a second. But we have some target, isn't it? Now, this equation, look at here, this equation may also give the similar solution, but it will not put any restriction on this. That it should be this particular value. We shall see later. In case of free particle, this is free particle equation. Then we shall add what you call our potential part. Is that okay? This is a free particle equation. Now look at here. We have to see this whole equation in a different aspect. Yeah, it's a differential equation, okay? But again, since we are touching this one to operator method and all later, which is developed by Heisenberg, okay? I mean matrix mechanics, and again operator algebra, that is what you call developed by Dirac, okay? That's why we have to see the whole equation in a quite different manner, okay? Now what is actually derivative? Okay, suppose if you have f of x equal to x square, you take derivative of the function, isn't it? What do you mean by derivative? D by dx of f of x, am I right? You say like that. What is that one? That is equal to 2x, isn't it? What is this d by dx? It will give you an instruction, isn't it? It is an instruction. This derivative is an instruction to do something. Take derivative of f of x with respect to x, isn't it? and you write the answer. It's a kind of instruction, it's a kind of operation. Can I say like this? You are doing something over there, am I right? It's a kind of operation. D by dx is a kind of operation, isn't it? So similarly, dou by dou t, I h bar dou by dou t. So we are going to see this dou by dou t as an operation. We are going to see this dou square by dou x square. Okay, it's a kind of operation. Later, I think in the next class, we are going to find that one. We define momentum operation. Operator corresponds to what you call momentum. We don't have any variable here. We don't define position. We don't define momentum here. We don't have any variable as a function of time here. Okay, we don't have any what you call position as a function of time, what you call, or momentum as a function of time here. Look at here. We have operators here, isn't it? Now this is a kind of operation. Can I say that's one a second derivative operator, dou square by dou x square? Isn't it? Now what I do is, again later we shall see, we are going to define momentum operator. Using that one you can find average value of momentum, some idea, something you can find. Okay. So now that momentum operator in case of one dimension, that will be minus I h bar dou by dou x. Let me argue later, okay, not here. So px actually, but let me write p in case of one dimension. Okay. So now look at here. So when you see this one, this second derivative operator is nothing but operating this momentum operator twice. Okay, this whole thing we can write it as, if you define momentum operator like this, I h bar dou psi by dou t, dou psi by dou t, that's equal to, look at here, p cap square, px cap square by 2m operating on, look at here, this is first derivative operator, am I right? You just write px cap square, operate it twice, minus I square, minus 1, am I right? H bar square, isn't it? Again, divide by 2m exists, operating on psi. Is that okay? Later we see that, yeah, this is a kinetic energy kind of operator, isn't it? It's not kinetic energy, it's an operation. Okay, it's an operation. We call it as kinetic energy operator. This p cap square by 2m, we call this as kinetic energy operator. Is that okay? Later we find, yeah, this is for free particle. In case of particle which has some what you call potential, particle under force field. Okay, so particle in conservative field, let me say like that. Okay, we take only conservative field here. Is that okay? So conservative field means you can write force is equal to minus del v. Okay, or in case of one dimension, force is equal to minus dou v by dou x. Force is derivable from the potential. Okay, let me explain this conservative field everything in vector calculus and electrodynamics. Okay, so I am taking conservative field. In case of conservative field, potential should exist. Am I right? Where to put that potential part? We are going to put that potential part here. Look at here. So again, if you have any potential, we are going to edit this equation. Dou psi by dou t, that's equal to px cap square by 2m of psi plus v of psi. Is that okay? Or you can say, you can rewrite this one, px cap, again v cap actually, this also operator. There is no variables here, everything is operator here. Okay, that operator will help us to find something. Okay, which we can verify by the experiment, that we shall see later. Okay, now this is equal to px cap square by 2m, so plus v cap, actually it's a function of x and t actually, usually. Okay, in the most general case, operating on psi. You have to see the whole equation in a different perspective. Okay, we call this one as Hamiltonian operator, because kinetic energy plus potential energy, in case of conservative system, that's a total energy, as well as this, we call that one as Hamiltonian, because this quantum mechanics, it is evolved from Hamiltonian mechanics. It has some evolution from classical what you call Hamiltonian mechanics. That's why we call this one as Hamiltonian operator. Hamiltonian operator, we are going to write h cap is equal to t cap plus v cap, that's equal to px cap square by 2. In case of one dimension, it is px, okay, by 2m plus v cap. Yes.
Sir, this Hamiltonian talks about energy, and this energy is, we are talking about classical one or quantum mechanical one?
No, quantum mechanical. The whole equation is for quantum particle only.
But this square by 2
No, this is the H is not variable here. H is not total energy here. It's an operator here. It's not variable. Hamiltonian is a total energy in case of conservative system. Okay, that's a classical physics. Okay, Hamiltonian is a variable in case of classical physics. Hamiltonian as a function of time, but not here.
Okay.
It's not. It's an operation now. You are doing some operation on this one. Is that okay? That's why again that operator is defined by this kind of cap. Okay, to say this is not variable, this is operator. Okay, this is not variable, this is operator. It will give some instruction. Okay, take derivative of, multiply by x. This kind of what you call instruction. Is that okay? So that's why this we call this one as time dependent Schrodinger equation. Okay. Now the best way to define the wave function is, what is wave function? Wave function is a solution of Schrodinger equation. Is that okay?